Okay, function operations. By function operations, what we mean for the most part, it's add, subtract, multiply, divide. You know, what do you do? How do you add and subtract and multiply and divide functions? You can see that if we go forward at the pace that I think we will be, then we're going to have a quiz on this unit on the 8th for this class, and the test will be on the 14th, which is like the week before we get to the Christmas break. So the function operations include the 4 operations that you already know: add, subtract, multiply, divide. And then there's one operation which is new, and it's in a way it's like the main point of this is actually this last thing that we have to learn how to do, which is called composition of functions. You know, I would say that for the add, subtract, multiply, divide, the important part is domain. It's a lot of it is about domain and being able to say what is the domain when you do these operations. Okay, so compositions. So here's addition, right? F of x equals 5x and g of x equals x plus 2. What do you think it means to say f of x plus g of x? I mean, you just add them up. I mean, your intuition would probably be right. You know, just add them up. I mean, or you could think of it like substituting, right? Substitute for the f of x what f of x equals. That would give you a 5x. And then substitute for the g of x what g of x equals. That would give you the x plus 2. Right? And then I combine like terms, 6x plus 2. Pretty straightforward. Now, these functions, 5x and x plus 2, are polynomials. What's the domain of all polynomials? It's all real numbers, right? I mean, remember, domain is all real numbers except those values that lead to restrictions, like divide by zeros, square roots of negatives. You know, nothing is going on when you do polynomials. Domain is all real numbers. So the domain of the sum of the two is still all real numbers, right? So the domain is all reals. All right, subtraction. You know, again, your intuition would probably be right. The tricky part about subtraction is if you're subtracting a function which has more than one term, you got to be careful about the minus sign, right? It's going to change the sign of everything that comes after that minus sign. So I'll substitute 5x, and I'll put minus, and I'm going to be careful to put my second function in parentheses. So that is 5x minus x minus 2. Right? Combine like terms, 4x minus 2. So that's the source of mistakes, you know, because we don't take into account the negative in front of parentheses. The domain, still, we started with domain, which is all real numbers, all real numbers. If you subtract them, it's still all real numbers, right? Domain. Okay. Multiply, I think. I don't even remember these sides. Okay. F of x times g of x. Again, we'll substitute. In place of the f of x, we'll put what it equals. In place of the g of x, we'll put what it equals. Right? And then we will simplify. 5x squared plus 10x. And again, the domain is still all real numbers. I mean, the result is a polynomial, and so it's still all real numbers. Okay, divide. Okay, now it gets a little trickier, because even though we're starting with two polynomials, right, when we divide, the result is not a polynomial. Right? If I divide f of x by g of x, now I have an expression in the denominator that could equal 0, and I got to make sure that doesn't happen. Which is the one value of x that's going to make that denominator equal 0? -2. So you have to say for the domain, x does not equal -2. It assumes that means it could be anything else, but it can't be -2. Right? Because if it was -2, you'd be dividing by 0. That's not allowed. Right? If I flip that, if I make a g of x over f of x, okay, now what's the one value of x that's going to make the denominator equal 0? 0, right? 5 times 0 would give you 0, so that you have to say x does not equal 0. We used to use one of the old released SOL tests, not the ones we're using these days, but it came from like an earlier version, and it had a question just like that. You know, it said, "What is the domain of this function right here?" And the right answer, it was a multiple choice. The way they worded it, they said, "all non-zero real numbers." And we missed that one every year. That was the most missed question because just the way they worded it. But in the end, isn't that what that says? All non-zero real numbers. That's the domain. Okay. So that's a divide. Now, those are just basic examples to show you. Now I'll get into that. I'm going to show an example, then you do the you try. Their examples in the book are not using polynomials. I mean, you could see these two polynomials are actually rational exponents. These are radicals. So that's not a polynomial. So find f of x plus g of x and then state the domain. So let's see, f of x plus g of x. Remember, you can't always add radicals. Can you add these radicals? Remember, what has to be true for you to be able to add them? The same index and the same radicand, right? Well, in rational exponent form, it means the same base and the same exponent. So yeah, they're both x to the 1/2. I mean, even at this point, you could think of them, we say like radicals, but these are like terms. Right? They have the same variables raised to the same power. So how do we add those? You add the coefficients, right? 4 plus -9 is -5x to the 1/2. Which I could write that like -5 times the square root of x. Right? Just a different form. Okay, now what's the domain of that? Is -1 in the domain. Can you plug in -1 for x? No, you can't, right? How about -4? Well, so what about -9? What about any negative number? No, right? How about 0? Can you plug in 0? Can you take the square root of 0? Sure. 0 times 0 is 0. So you have to say that the domain is, how did that just happen? X is greater than or equal to 0. You have to take whatever's inside the square root, set it greater than or equal to 0. It may be that it's like an expression that you've got to then solve to see what those x values are. In this case, x was all there was. So the domain is x greater than or equal to 0. Okay. I'm going to skip ahead here and see. Okay. So here's our subtract. And the subtract is not going to be too much more interesting than the add. F of x minus g of x is 4 to the 1/2 minus negative 9 to the 1/2. Sorry, x to the 1/2. X to the 1/2. Right, which is 4x to the 1/2 plus 9x to the 1/2, which is 13x to the 1/2. And the domain, anything different about this one than the last one in terms of domain? It's the same thing, so just say x greater than or equal to 0. Let me see how much does this say. Got 1 hour and 59 minutes left. Ooh. Okay. So here's your u-try. There's two functions, f of x and g of x. Do the f plus g and do the f minus g, and then state the domains. Right, so for the sum, you just add them up. Add up the coefficients. 5x to the 2/3. Okay, what would you say about the domain of that? What kind of radical is that? Come on, on Wednesday, you take this test. If you can't answer, what kind of a radical is it if it's to the 2/3 power? It's a cubed root, right? Because of the 3 in the denominator, okay? So what's the domain? All real numbers. Remember, you can take the cubed root of a negative number. You can't take the square root. So this one is going to be all reals. Domain is all reals. And the f of x minus g of x is going to be negative 2 x to the 2/3 minus 7 x to the 2/3, which is negative 9 x to the 2/3. Right, and domain again is all real numbers. Okay, multiply. Okay, so let's see. F of x times g of x equals 6x times x to the 3/4. Okay, now how am I going to simplify that? What do you do with the exponents? You add them up, right? I mean, it's just different exponents. I mean, in this case, the exponent is 1, right, which is like 4/4. So this should be 6x to the 7/4. Okay, now what is the domain of that? Again, what kind of a radical is it? It's a 4th root, okay? Is 4th root going to be all real numbers, or is it going to be limited? It's limited. Remember, all the even radicals, the domain is x greater than or equal to 0. Or you can only take the even radical of a number greater than or equal to 0. So we have to say x is greater than or equal to 0, right? Because of that 4 right there. Right? If it's an odd number, you're going to say all real numbers. If it's an even number, you're going to say x greater than or equal to 0. Okay. Okay, now we do the divide. So f of x over g of x. We're not doing both, we're just doing the one, right? So f of x over g of x. Right? The f of x is 6x. The g of x is x to the 3/4. Okay. All right, how can I simplify that? Well, just before you do that, because I know that this is the way this is going to work out. What would you say is the domain of the g of x right there? Okay, but it can't actually be equal to 0, right? Because if it was, then you got the other problem. You're dividing by 0. So when you end up with a radical in the denominator like that, you've got to say not just greater than or equal to 0, but greater than 0, right? And you know that wouldn't happen if it's in the numerator. So I'm going to start this out and just say that in this right here, we would have to say the domain is unsimplified. We're going to say the domain is x greater than 0. Then the truth is, we can simplify that, right? What do you do with the exponents when you divide? You subtract, okay? But this time it's going to be 1 minus 3/4, which is going to be 6x to the 1/4. Okay, now, just looking at that there, with the x to the 1/4 in the numerator, I would think, well, that's greater than or equal to 0, right? I don't have the divide by 0 thing. But because we started this by dividing, we still have to say it's greater than 0. Right? When you have like one part of your, this process that has a limited domain, you got to stick with it. Even though at the end it might look like it canceled out, it's still in there. What would I get if I just went up to these first? What if I said, what is f of 0? What would you say? And what is g of 0? And so f of 0 divided by g of 0 would be 0 over 0, undefined. So we have to take into account that it cannot divide by 0, even though it looks like that's simplified away. Okay. So here's your u-try. There's the two functions, and try to multiply only and state the domain. So what is the domain of f of x? All real numbers. What's the domain of g of x? It's an odd root, right? That's all real numbers. So when you multiply them together, x to the 6/5 is still an odd root. It's a 5th root. So the domain is still all real numbers. All reals. Okay, same two functions. Now we're going to do the divide. So just looking at it, unsimplified at all, what's the one value that x cannot have? 0, right? It's a fifth root, so it can be less than 0, but it cannot be 0, right? Because in the denominator, you're dividing by 0, right? Now, I can simplify that, and that's 5/5 minus 1/5. That's 3x to the 4/5. But I still have to say that domain is x does not equal 0. I don't like that 0. Yeah.
Why is this one x does not equal 0, but the one that we did in the example was x greater than 0?
Because this is an odd root. Right? You could take the fifth root of a negative number, but you can't take the other one was like a fourth root. You can't take the fourth root of a negative number, so that's why it had to be greater than or equal to 0. Or x does not equal, well, how did we say x greater than 0? So let's see, go back. Yeah, because it was a fourth root, that had to be greater than 0, because you can't let it be negative and you can't let it be 0. But this one is a fifth root, so you can let it be negative, but you just can't let it equal to 0. Okay. For a white rhino, heart rate R, beats per minute, and lifespan S in minutes are related to body mass M, kilograms, by these functions, right? Again, note that this notation, R parentheses M, means R of M. It's a function. They're just saying R is a function of M, and S is a function of M. So they say, let's multiply these two and see what we get. And so R of M times S of M equals 241. M to the negative 0.25 times 6 times 10 to the 6th, scientific notation, m to the 0.2. Right? Now we can multiply those. Let's see. 6 times 241. I'll take it in steps, even though we could do all this at one time. 6 times 241. 1446. Times 10 to the 6th. And then what do we do with the exponents? Add them up, right? You're multiplying the same base, different exponents. That looks like negative 0.25 plus 2, negative 0.05. Now we can, scientific notation, we wouldn't have this first number be a number that's outside of the 0 to 1. So if I move the decimal place over 3 times to give me 1.446, right, what does that do to the exponent of the power of 10? It goes what? It goes up 3, right? Since we move the decimal place over to make that number, the first number smaller, then the exponent must be getting bigger, so it must have gone up by 3. And that's m to the negative 0.05. I mean, actually, I could write it like this. I could say that's 1.446 times 10 to the 9th. Then I can flip that to the denominator, make that m to the positive 0.05. Okay, now what does that represent? If you multiply something that represents the heart rate in beats per minute times lifespan, which is in minutes. What do you think that's telling you? Where's my thing? Right, beats per minute times minutes, and actually the lifespan, that's not just any amount of minutes, right? That's the minutes for a life. That's minutes per, I'll just say it like this, life. So, you know, multiplying those two means the minutes cancel minutes. And what did we just figure out? This is how many heartbeats you would expect in the whole life. I don't know whether you had much experience with like canceling units and things like that. I mean, when you get to chemistry, you do that kind of stuff all the time. Maybe some other science classes you do that. So multiplying the heart rate times the lifespan, since they're both in the same units, minutes, it's going to give you how many total beats this white rhino is going to have. How am I doing on my time here? 127. Okay. Okay, then we get to the big one, right, which is composition of functions, right? A composition of functions is taking the function of a function. It's putting one function inside of another function. So I've written it here as f parentheses g parentheses x. So we've taken this g of x function and put it inside the f function. And the way you say it, you say f of g of x. Right? If I could do the opposite, I could take g of f of x, right? I could put the f inside the g, and we'll end up doing both for sure. But just for this one, the f of g of x, the g function has a domain and it has a range, right? So the g function maps the domain to a range. But that range ends up being the domain of f. And so then the f is going to take that and map it to its own range. Right? So the domain of that inner function is the range of the outer function. One plugs into the other. Now this vocabulary like inner function, outer function, that's just me as having a way to say it. I don't think the book uses that, but to me the one that's inside the other function I'm just going to refer to as the inner function, and the other one I'll call the outer function. Okay. Good. Okay, so here's two functions, f of x and g of x. Find g of f of 3. Okay, so the first step, find f of 3. If f of x equals 2x minus 7, how do you find f of 3? Right, you plug in the place of x, you put a 3. Right, so f of 3 equals negative 1. So we can replace that now. That'll be g of -1. Right, so the output of f becomes the input to g. Okay, how do I find g of -1? I plug in -1 for x, right? -1 squared plus 4 equals 1 plus 4, which is 5. So g of f of 3 equals 5. So try that one. Right? There's your two functions, and you're going to find 4 different things, right? You're going to find g of f of 5, f of g of 5, f of 5, and g of 5. Remember, the starting point is evaluate the inner function. So what did you get on the first one? 98. Second one? Say again? F of g of 5. Anybody? What is that? It's going to be f of g of 5 is going to be 2 times 5 squared, right? Which is going to be 2 times 25, which is 50. So that's like saying, what's f of 50? And that would be 142. Okay, how about the f of 5? Let's see, f of 5 is 3 times 5 minus 8, which is 7. So we have to say that's f of 7. And then we can just go back to the same equation again, right? That's 3 times 7 minus 8, which is 13. Okay, same way with the g. We already found g of 5, right? So we just need to do this again. What's g of 50? Right, that should be 2 times 2,500, which is 5,000. Okay, so we're doing compositions, but so far, all the compositions we've done, they've given us like a number, right? That's not always the case, and it's probably the harder of it is when they don't give you a number. And that's what I think the next examples are. Right? So now it doesn't say find f of g of a number. They're saying find f of g of x. So we're going to actually have to be like putting one function inside of another function. So let's see, the inner function in this case is the g of x. Let me scoot this down so we can see it. So since g of x is the inner function, I got to take this right here and put it in the place of x here. So what's that going to look like? F of g of x, right, is going to look like 4 times 5x minus 2 raised to the negative 1 power. All right, now what is the, how can I simplify that? What do we do with negative exponents? Flip. So that flips 5x minus 2. Okay, now what was the domain of g of x? Just considering this right there. What would you have said the domain is? It's all real numbers, it's just a polynomial, right? But now that 5x minus 2 is in the denominator, and we cannot let that denominator equal 0. So how am I going to find the domain? Right? I have to say that 5x minus 2 does not equal 0. Right? Which means 5x does not equal 2, and x does not equal 2/5. I mean, we did this with polynomials, right? How do you find the zeros of a factor, right? You have to figure out what would I plug in for x there. I mean, you don't necessarily have to set up the equation. If you can see that 2/5, the 5s would cancel and 2 minus 2 is 0. So it is important that g of x, actually the domain was all real numbers. But f of g of x, the domain has to be x does not equal 2/5. Ready? So, did I skip one? Seems like I skipped one. Okay, now we're going to find g of f of x. And these are the same two functions. Right? So I'm going to go, this time I have to take the f and make it the inner function. So I've got to take this, and I've got to put it in the place of x right there. So g of f of x equals 5 times 4x to the negative 1 minus 2. Okay, simplify. All right, this is going to be equals 20 over x minus 2. So what is the domain? Right, what's the one value of x that's going to lead to a divide by 0? 0, right? You're dividing by x. 0 is the 0. Remember, just like again with polynomials, when you had a factor with just a standalone x, then 0 is the 0. So x does not equal 0. What was the domain of f of x, by the way? I mean, 4x to the negative 1 would have been 4 over x, so it's still been x does not equal 0. Okay, now we're going to do f of x. Okay, so basically you could say, maybe it would help in this case to do it like this. I'm going to write myself another f of x equals 4x to the negative 1. And then I got to take this f of x and put it in the place of x there. Right, that'll look like this. F of x equals 4 times 4x to the negative 1 to the negative 1. Okay, what was the domain here? What's the domain of f of x for x to the negative 1? Domain is x does not equal 0. Okay, now let's do this here. How do I simplify? Well, first, what do I do with this negative exponent? I distribute it. So that is 4 times 4 to the negative 1 times x to the first, right? And this 4 over, this is going to be like 4 over 4 times x. So the whole thing gives you x. So f of x equals x. Okay. Now, if I'm just looking at the function y equals x, what would I say is the domain? Right. If I'm looking at just y equals x, what kind of a function is that? It's linear. It would have a domain of all real numbers. But you have to take into account that you don't get to that function except by going through that inner function, f of x. And what was the domain of the inner function? It was x does not equal 0. So you have to say for the composition, the domain is x does not equal 0. You can't just look at the final product and ignore how it's actually put together. Right? You start by plugging into one function, and then you take that output and you put in the other. But you can never plug in a 0. Right? You can't get started because you can't plug into f of x a 0. So you can't plug into the composition a 0. Right? So we still have to say that the domain, despite that it doesn't really look like it would apply, it still has to be x does not equal 0. And that is because of this. I think my next slide, I point that out. Nope, that was wrong. So the domain of the composition must include restrictions to the domain of the inner function. Right, so try to do your compositions and domains for these two functions. 2x to the negative 1, that's f of x, and g of x is 2x plus 7. Compositions and domains. So I mean, this is very similar to the one we did on the last slide, the last couple slides there, right? For the first one, f of g of x, since g of x is the inner function, you put it 2x plus 7 into the place of x here. So what did that look like? 2 times 2x plus 7 raised to the negative 1. Right? We replace the x with 2x plus 7. Simplify. Flip it to the denominator. Can't divide by 0, so x does not equal negative 7 halves. Right? G of f of x, now we got to take 2x minus 1 and put it in the place of x there. So 2 times 2x to the negative 1 plus 7, which is 4 over x plus 7. Again, domain x does not equal 0. And the last is f of x. Put the 2x minus 1 in the place of x in that same function. So it's 2x to the negative 1 raised to the negative 1. Distribute the negative 1 as exponent. Simplify, and we get the same as we did on the last slide, x. Which, again, you wouldn't think that has a domain, but since the inner function f has a domain of x does not equal 0, then so much must the composition. You've got to take that into account. So one last slide. So you have a $10 gift certificate to a paint store. The store is also offering 15% off your entire purchase. You decide to buy $55 of paint and supplies. Use the composition of functions to calculate how much you will pay if you use the $10 gift certificate first or you use the 15% off first, right? So let's see, how would I do the calculation if I'm going to do the $10 off first? So we're starting with a cost of $55, right? And then we're subtracting the $10. And then how is it that I apply a 15% off? Multiply it by what? Yeah, 0.15 will give you the discount, but if you want to know how much is you actually pay, multiply by 0.85. If it's 15% off, that means you're paying 85%. Okay, that would be taking the $10 off first. Now, what if you did it the other way? Then you would start with 55. You would multiply by 0.85. And then you would take off your $10. So let's do the math. Clear. 45 times 0.85. 38.25. And 55 times 0.85 minus 10, 36.75. Right, so which is the best way to do this? Yeah, take the 85% off first and then take off the $10. So this is the best way. I'll call that a best buy. Not to be confused with the store. Okay. Okay. I mean, that's a practical example of using compositions, one function inside the other. Okay, I think I'm done. I haven't worn out my battery quite yet. Function operations. We described restricted domains and ranges. That's part of the SOLs. And a composition of two functions. Find the composition of two functions. That's the homework. It's a fair number of problems. They're all odd, so you can check all the answers. Like I say, some of this, I think, as we went along, you could say, well, you know what? It did kind of relate to what's going to be on the test. I mean, this is section 6.3 in the textbook, so it comes right after 6.1 and 6.2, which are on our test. But it's not all. I probably wouldn't want to get too deep into this if you really just want to prepare for the test. But I'll leave it up to you. Okay.